All right, so quick check-in. How is everybody? It's week 4. Better than alive? That's awesome, but it is week 4, so you probably shouldn't be. Okay, any questions? So we have this midterm coming up on Thursday. All okay? Yeah.
Just to be clear, because in the course manual there are also some suggested exercises about limit calculation and stuff. We will not be able to
No,
calculate.
you do not have to calculate any limits.
Okay.
Yeah. All right. Then today we're probably not going to get through all of this, but what we will hopefully get through. So I'm going to just do a recap of iteration of double integrals, because that's quite a big part of the midterm, so I thought it'd be helpful. And then talking a little bit about improper integrals. So you'll remember from calculus 1, sometimes you want to take the limit, you want to take an integral from, say, 0 to infinity, and that infinity thing is improper. And we need ways of handling that, so we need to do that for double and triple integrals. We're going to talk a little bit about polar coordinates. So there are times when it is very useful to not work in our usual x, y, z coordinate frame. Then we're going to skip quickly to triple integrals, because double is never enough. But I'm not going to spend a lot of time here, because a lot of what we've covered in double integrals is immediately applicable. It's just now you're doing 3 integrals instead of 2. So it's like even more fun. Then we will basically, that brings us to the end of the section on, no, don't do that. Okay, this is not great. Maybe. Nope. Yes, no. New iPad. Will it come back? Okay, that's interesting. Yeah. Let's see if maybe this works. Okay. Wait, let me try this. What? Oh, dope. What's this? Okay, it's going to be interesting, but maybe. Yay! Okay. So long as I huddle over here, we should be fine. All right, so we've been talking about double and triple integrals, and really we've been thinking about functions of 2 or 3 variables, so something that takes in a vector and spits out a number, and we've been dealing with all that kind of thing. But then we need to move on to the next section, which talks about vector and scalar fields, where we're dealing with functions which take in a vector and spit out a vector. And we need to do all the things associated with that. So that's where we're starting. I think we will probably get up to about here. We might talk a little bit about conservative fields. I very much doubt we'll get to line integrals. But just so that you know, this is sort of where we're headed. Okay, so just to recap, we have this idea of a double integral. So you've got some surface living in x, y, and z, and you want to find the volume underneath that surface over a particular domain. And we had a little look at how you do that and how you build up the ideas, but just like in calculus 1, you didn't do everything from first principles. You learned tricks in how to do things very quickly. We learned some tricks for how to deal with double integrals. And one of those is this thing over here, which is not mentioned here, but it's called Fabini's theorem, which basically says if you have a nice, well-behaved function f of x, y, so continuous and bounded, all the things we usually have, then we can split it up, if we're looking over a particular domain, into an integral with respect to dy and an integral with respect to dx, or the other way around, depending on the kind of thing that we're looking at. Much easier seen with an example, so let's have a look. So I usually write my integrals, and you'll have seen me doing this, as something like this: 0 to 1 root x 1 e to the y cubed dy dx. So I don't put my dx here, I put it on the outside there, just so that I know that when I'm integrating, the first thing that I'm doing is I'm integrating this in a bit. So I need to do the integral of e to the y cubed dy with respect to y from root x to 1. And then whatever I get in there, I'm going to integrate from 0 to 1 with respect to x. And the next thing is I have a look at this and I go, well, I have no clue how to integrate e to the y cubed with respect to y. Like, I got nothing. Okay, it looks like it should be super simple, but there's no rule that's going to help you here. You can try it by parts, you can try it by substitution. It just gets horrible. And if you were just stuck with doing that integral, then basically you would be stuck. But because we have double integrals, maybe we can change the order and it'll make life better. So how do we change the order? Well, what we need to do is we need to change these limits so that I can integrate first with respect to x and then with respect to y. So our outer integral always just has numeric limits going from 0 to 1, whereas our inner one has some functions of the other variable. So just to be clear, our limits at the moment, our limits of integration so this bit is referring to y. So that says y goes from root x to y is equal to 1. And these limits say that x goes from 0 to x is equal to 1. And we'd like to find new limits so that we can integrate with respect to x first. So the trick here is to draw out the region which these 4 lines give us, because that's our domain, and then think about how we rewrite that so that we have x is some function of y instead of the other way around. So let's sketch that. So here's our xy plane. Okay, so the line y is equal to root x, what does that look like? It's not this one, it's this one.
Yeah, this one, yeah, that was
yeah. Okay, all right, so it does something like that. Okay, so there's our line y is equal to root x. So it goes from there to the line y is equal to 1. Okay, so here's the line y is equal to 1. And where do these two intersect? At 1. Okay, so we know that this point here is 1. Okay, and now we go from, and I'm just going to do some colors so we can see. So we have those two. And now we have from x is equal to 0. So which is the line x is equal to 0?
the y-axis.
The y-axis. Okay, I always get it wrong, so that's why I'm asking you things. So it goes from y, so this is x is equal to 0. X is equal to 0 everywhere on the y-axis. Okay, to x is equal to 1. So if we look at the region that is encapsulated by all 4 lines, it must be this region in here. So that's the region that we're integrating over. So now what we want to do is we want to integrate with respect to x first, and then with respect to y. And we want our y's to be the limits that just go from a number to a number, and our x to involve some function of y. So let's put the y limits in first. So if I look at this region, what constants should I be integrating y from to?
0 to 1.
So it should go from here, from 0 to there, so it should be 0 to 1. Okay? And now if I look at x, x needs to go from here, which is x is equal to 0, but it needs to go up to this line here. So we need this line expressed with x as a function of y, which we can do quite straightforwardly. We can just solve this one. This says that x is equal to y squared. So we know that we're integrating x from 0 to y squared. Make sense? Let's see what that does to our integral. So if we rewrite this, now we've got our 0 to 1, but this is referring to y, not x. And we're going from 0 to y squared, e to the y cubed, but we're integrating with respect to x first and then with respect to y. So it doesn't look initially like much has happened, but a lot has, because we're integrating this thing, which we didn't know how to do before, but now we're integrating with respect to x, and x doesn't care about y. It sees it as a constant. So this whole thing, as far as this integral is concerned, is a constant, which is very nice. So we get 0 to 1. We can in fact just take this out. And now we're just integrating from 0 to y squared dx dy. What's the integral of dx with no integrand? It's just x. So we've got so that's just going to be x, which is integrated from 0 to y squared. And so we end up with, well, x evaluated at y squared is just y squared. X evaluated at 0 is just 0. And look at that.
It's y cubed.
Yeah. And now, suddenly, look, this is delightful. If you could see that that was a 3. Because you can just do this by integration by substitution. And it's done. So often what happens when you'll write down your double, or in fact triple integral as best you can, that you need for whatever problem you're trying to solve, and then you look at it and you go, that's hairy, I can't handle that. And then you think, can I change my order of integration so that it is something that I can handle with? Okay. And the whole key to this, so I'm going to put ... You can check for yourselves. The answer is 1/3 e minus 1. And in here we have some substitution. Okay, so check that for yourselves. So the whole key, and I still do this for myself, is I write out my box like this of my limits from the thing that I've got. Then I draw my region like this, and then I use that to redo my limits. Okay. Yeah? Sweet. Okay, so we want to, so I will come back to these examples, otherwise I'll put them up in the notes. Did I draw a picture of this? Just see what I wanted to say here. So I think we won't work through all of this, but I want to talk through a little bit about how you would go about setting up the integral here. It's a volume, so we know that we're going to be basically integrating some surface over some domain, but we need to kind of get a picture of what that domain is. So the issue here is how, if I just get given a problem like this, how do I set up the integral? So let's try and think a little bit about what this shape is doing over here. So this gets tricky, and I would draw it in GeoGebra if I was you. I think I might have it, so I don't. Okay. So the plane y is equal to 0. Which plane is that? It's the xz plane. Okay. So we've got x and y and z. So that's this plane here. Maybe easier if I do this. Okay, so we know, but it's also the negative bit. I'm just not showing it because it gets too complicated. So we know it's everything bounded either on this side or that side. At the moment, we don't know. Z is equal to naught, which is that? XY plane. Okay. Okay, so we've got this plane and this plane. And now let's look at the parabolic cylinder. Where does that live? Okay, start by going, okay, where does y, if you just think about y equals a minus x squared over a as a parabola, where does that live? In the xy plane, and what does it look like? So maybe we can draw the xy plane. What does that parabola look like? So is it a happy parabola or a sad parabola? It's a sad parabola.
And
Where does it cross the y-axis?
in A.
At A. Okay, so it's doing something like this. So it's got an A there, and you can check it's A and minus A there. Okay, so if we put that, let's give it a different color on here. If we put that into this diagram over here, then it's doing something like that. So let's just give, yep. Okay, plus, I mean, it has bits coming out down there and down there as well. But it's a parabolic cylinder, so we have to think about it in 3D. So all we do is we just, for every value of z, we have this. So it's basically a curve that is running up like that. Okay, so you have this thing doing that. Okay, so far what we've done is we've got our plane here that we're working on, we've got our line here, and we've taken out a chunk over here, but at the moment we don't have a top. So at the moment this is just carving out kind of a, not quite as a half cylinder, but a half cylinder shape. Yeah? So the final thing is we need this plane, z is equal to a minus x plus y. And that's a little tricky to visualize, but it is a plane that kind of comes like so and cuts off our cylinder a little bit. So I want to see if I can find a picture. That's not it. Okay, okay, I'm not going to find a picture. You could sketch, for example, where our plane cuts the xy axis. So when z is equal to naught, we've got the plane naught is equal to a minus x plus y. So when z is equal to naught, we have y is equal to x minus a. Yep. So if we looked on the xy plane, what we would be seeing is it cuts like that. But, so to think about, okay, the domain that we are integrating over, we need to combine all this information. So what I'm interested in is, firstly, what is my domain here? And then how do I put my limits together? So if I have a look at this, remember we have the line y is equal to 0 is one of our limits. So let me put this in a different color. Y is equal to 0 is this line here, or equivalently that line there. And then we've got our parabola. We also have this line over here, which doesn't actually seem to be affecting anything at all. It's not changing that inner size at all. And the final thing that we need to think about is what happens to our z is equal to 0 that's not impacting at all. So in fact, the only constraints that we have that are affecting our domain are this y is equal to 0 and this parabola. So our domain of integration is going to be that space there. And we're going to be integrating that up to the plane, wherever the plane is. Yep. So then we can put it all together. And you know that you're going to be integrating, so you can decide on your order. I think it's going to be easiest to integrate y first. So we're going to integrate y from 0 to, what's this thing? A.
Sorry, Claire.
Yep.
Y equals to x minus a made you conclude that we don't care about z being a bound. Like, why? I can see it on that graph, but why do you do that line? Like, what is it?
So I put that line in because if, for example, it had been a plane that cut the axis like that, then because we need to have all of the constraints where over the region where everything is met, it would only be this little region.
Okay.
But it happens that we have cunningly chosen that it just,
Okay.
Yep.
Mm-hmm.
so it doesn't affect our region at all.
I see. Thank you.
Okay, so I'm integrating with respect to y first. I'm going from 0 to here, and then I'm going to integrate x from minus a to a. And the thing that I'm integrating is my surface that is topping everything off, so that's going to be a minus x plus y, and it's dy dx.
Can you explain one more time how did you get the thing like this green region?
Okay, so I know that I've got some region on the xy plane that I'm going to integrate over. And I've got my plane that I'm integrating up to. And we know that for double integrals, I need to be able to describe that domain that I'm integrating over. So that's what I'm looking for with the green thing. So what do? I say, what are my constraints? Well, y is equal to 0 says I have to lie either on this side of that line or on that side. So initially over here, it was either the top half or the bottom half. Okay. Z is equal to 0 says that I'm integrating from the xy plane either up or down. So it doesn't change this at all. I'm going to come back to that. Looking at this, I know that this has to be true, and so I sketch this. And so I look to see what region combines this and this. So it combines the blue line and this, yep. And also is going to be above. So if I think about Z coming out here, is that the right way around? Yes, Z coming out here. I know that this plane is coming up, so it must be that region. And then just to be sure, I sketch this line, which is when Z is equal to 0 for that plane, to check that the plane isn't cutting somewhere here, which means that my region would be smaller. Yep. Okay.
If the plane has been cutting somewhere in the middle of the curve, I should have looked for the intersection between the curve and the plane too, right?
Right, so if the plane was cutting here, then it becomes a nuisance, and what I would do is I'd probably integrate from here to here, just using, and then I'd look at, and then then I'd have another integral where this was my y limit, so the blue was the y limit going to the purple y limit.
Okay.
That's what happens when you're increasing Z. Like the plane is within, it goes into the cylinder.
Yes, but it is not, but the domain that we're integrating over, so that is taken care of when we do this integral here of this thing. Yeah. Okay. There'll be plenty of practice in the tutorial today. Yay! Okay, I'll put up full solutions for those. So, a brief discussion of improper integrals. But we are not, in fact, so I'm going to just do this as for interest only. It's not necessary for the rest of this course, so it's coming out. Improper integrals, let's have a look and see what happens. So we've got here e to the minus x squared, and we want to integrate over the region where x is bigger than 0 and y lies between minus x and x. And it says see figure 1520, but for practice we'll just draw that. So x is bigger than 0, so what does that give me?
No, the y-axis.
Yeah.
The y-axis above.
So x is bigger than 0 says we have to live. I don't have that in. Says we have to live here. Okay, so we know, so that constrains us to living here. I find two inequalities difficult to visualize, so I usually split these up. So this says y has to be bigger than or equal to minus x, and y has to be less than or equal to x. Okay, so the line y equals minus x looks like that, and y is equal to x looks like that. So we want the region where x is bigger than 0 and y is greater than minus x, so up here, and less than x. So this is our region here. And it's the region that just keeps getting bigger and bigger and bigger. So if we think about what are our limits here, let's think about our okay, so tell me my y limits first, because those are straightforward. Minus x to x, so that's not a problem. And x integrates from?
0 to infinity.
And right away here, that's a problem. So in calculus 1, what did you do when you had a limit that went to infinity?
You put a parameter of t and then you calculate the limit for t that goes to infinity.
Right. So you would have written something like, instead of having the integral from 0 to infinity of t dt, you would rewrite that as the integral from 0 to r of t dt, and then you take the limit of that thing as r goes to infinity. Does that sound familiar?
Yeah.
Yeah, and either the limit would work, in which case yay, or the limit would say, actually it's unbounded, in which case the integral doesn't exist. Exactly the same thing here. So let's just work this through, just so that we get a little bit of practice. So let's set up our integral. So the way we've got it set up here, we need to integrate with respect to y first, because that has x's in it, and x just has our constants. So our integral is going to be equal to okay, and with joy and delight, we look at the e to the minus x squared, which we wouldn't be able to integrate with respect to x, but we totally can with respect to y. So now I've got e to the minus x squared, and I've got my integral, so I've got y from minus x to x. Okay, and this is the, is it 2x?
X plus minus minus x?
2x. Thank you. Okay, and how do I integrate e to the minus x squared times x? Substitution.
Minus x squared.
Okay, so let's u equal minus x squared. Whoops. du is minus 2x dx. All good so far. So I've got a minus, I'm probably going to get this wrong.
No, wait.
Minus 1.
I would have done it actually another way.
Mm-hmm.
If you keep the 2 inside the integral,
Yeah, they're
and you
going to.
multiply you multiply by minus inside the integral and by minus outside, then you just have e to the
Yeah.
power of minus x squared times its derivative.
Yeah.
So the integral just e to the power of minus x squared with the minus in front because you
Yeah.
multiply it 2 times. So it's minus e to the power of minus x squared
So it's e to the power.
of minus x squared. Yes.
Yeah, I mean, it doesn't matter where the 2 is.
Yeah. E to the power of minus
Yes,
x
but
squared with the minus in front. Everything. Minus e to the power of minus x squared. That should be the integral. Yeah.
Okay, but we're changing.
Oh no, we changed the variable. Okay.
We need to change variables. Yes, no?
It's e power u by u equals
Oh yeah, true.
say minus e power u by u equals minus x squared.
Okay, I think.
Just do insertion into the differential, right?
Okay, however you've learned to do this is fine, so long as you get the right answer. I'm just going to do this. Okay, so I've got e to the u du, and I think we get a minus sign.
Yeah.
Okay, and but the important thing here is I need to change my limits. So when x is equal to 0, what is u equal to?
Also 0.
Also 0, okay. And when x is equal to infinity, what's u equal to? Minus infinity. Okay, so we go from did I write that down? What have I written here? Oh wait, no, that was right. Yeah. Okay, so we go from 0
Choose the other way around.
Well, be careful. We keep it the way it was. Our lower limit was 0. So in fact, then we flip it.
Oh,
But we need to remember then we take this minus sign away.
okay.
If you go in the opposite direction, you get negative. Yes?
Yeah.
Yep. Okay. We're getting hung up in the details here, which is minus infinity to 0, e to the u du. Yep. Okay, go and revise single integral limity thing, crazy changing things if you need to. Okay, pure integral of e to the u. Okay, e to the u, great. Okay, so we've got e to the u minus e to the e to the 0. Okay, and e to the 0 is 1. E to the minus infinity 0. Yay! So this one converges. So in this case, we didn't end up having to take any limits in the sense that you already know how to deal with this. So there is limits hidden in here, but it's hidden in your brain that you're automatically doing this stuff. So good job. So you can read a little bit about that. But let's have a look at this example over here. So we need to decide, can we actually integrate this thing? So we want to integrate 1 over xy, where our region is in the first quadrant, and it lies between the line y equals x, which is this bunny here, and the parabola y is equal to x squared, which does something like this, and they cross at 1. So this is our region here. So we can set up our integral. So how shall we integrate it? Who shall we integrate first, x or y?
Doesn't
It doesn't matter. I think it's going to, because of the amount of time we've worked with y is equal to x squared, it's going to be easiest to go, we know that our lower y limit is this, our upper y limit is that. So we might as well do those first. So let's do dy dx. So then we've got, here's our lower limit, that's y is equal to x squared, up to y is equal to x. And then my x limits will be
0 to 1.
0 to 1. Right, so you would just check what that intersection point is. Okay. All right, so let's go ahead and do this. All right, so I'm integrating 1 over, yeah?
Why don't we consider the region past x equals 1? There's still space bounded between the...
Specifies first quadrant of the
It's still in the first quadrant. There's still space between the lines y x equals y.
It says it wants a bounded region.
Yeah.
Okay, so I'm integrating 1 over xy with respect to y. What do I get?
1 divided x ln y.
Right, so we've got
Absolute value.
our y doesn't care about the x, so we've really got a 1 over x, and then we're integrating 1 over y, which is the natural log of absolute value of y, and now we integrate that with respect to x. Oops, and we need to have some limits here going from x squared to x. So this is going to give us natural log of x minus the natural log of x squared. And you can use your delightful log laws.
Oh yeah.
Yes?
1 divided by x.
You can simplify this down.
Yes.
Okay. Anyone know how to solve this?
Substitute 1 of x equals u.
So you can do that. The equivalent is saying let x is equal to e to the minus t.
Yes.
Okay, I'm going to let you play around with that and get back on track. And you're going to end up with an integral that goes from 0 to infinity of t dt. And what can you tell me about this? Converge, diverge.
Can you explain more explicitly how you went from this one to this one here?
From which one? This one.
Let's, yeah, I don't
No.
understand.
So you need to go back and revise substitution.
No,
Okay, so yeah, if you're feeling hazy about the substitutions, please go and revise. I'm not going to give you hairy ones, but you do need to be able to do our basic substitutions. Okay, but talk to me about this integral here.
That does not convert.
Does not converge. Okay, so you could work it out. You could say, okay, let's do this. Let's say is equal to the limit as r goes to infinity, integral of r of t dt. Integral of t is, okay, so we've got a half r squared. Okay? And then if you take the limit, that goes to infinity. So that's the formal way. It's enough for you at this point over here to go, we know that that diverges, so we can't find an answer. Okay. Yeah.
So on the exam, if you have like an integral like this, if we just say divergence, that's fine.
Mm-hmm.
If we get to like an integral like this, we
So if you get here,
yeah.
and you
And then we just like put like an arrow and just say divergence.
yes, that's fine. Yeah. So long as that's right. So be secure in your statement. Yeah.
Shouldn't the ln be ln of 1 divided by x?
No.
Why not? Isn't the Because we should do ln of x divided by x squared.
Ln of 1 divided by x is minus ln x for log x.
Ah, that's where the minus comes from. Okay.
Okay. Okay, so I think some revision on substitution and playing around with logs. Yes? Yes. Okay. All right, so you can read about the mean value theorem for double integrals. You'll notice that it's a mean value theorem. There are many, if you're interested, but not going to be necessary for what we're doing for the rest of this course. So I'm going to leave that for you. Okay. So, suppose I handed you this integral over here. So we want to find the volume of the solid region lying above the xy plane, beneath the paraboloid. If we wrote this up and spent some time, you would end up, like if you sketch things and drew the regions and stuff, you'd end up with this integral over here. And I mean, I feel it's very unfair to ever say this to anybody, but this is not pretty, okay? That makes my heart go, oh, don't make me do that. But luckily, thinking about the situation, so we've got a paraboloid, there's a whole lot of circular symmetry going on. And this is where polar coordinates can really make our lives a lot better. So what we're going to do is change coordinate systems. Instead of expressing things in terms of x and y on the xy plane, we're going to express them in terms of r, the distance from the origin, and theta, the angle from the x-axis, going clockwise. So in order to do that, we're basically literally going to translate every integral from being in x's and y's into r's and thetas. And we need some way of translating between the two. Well, you know that your trig, x is equal to r cos theta, y is equal to r sine theta. And then thinking about going in the other direction, we know that r squared is just x squared plus y squared, so that's useful. And tan theta is y over x. Okay, how does this help us? Let's head back to our thing over here. So we've just said that we're going to convert this step by step into things involving r and theta, not x and y. So the first thing to do is have a look at the integrand, the thing we're integrating, and you can see that there's a 1 minus x squared plus y squared, but that's just r squared. So we can change that over there. So that bit has now changed into an integral with respect to r squared. But the thing that we haven't changed yet is we need to think about what our dA is, our little area is. And in order to do that, we know that in Cartesian coordinates, our area is just little dx times little dy. But if we're thinking about this in polar coordinates, it doesn't make sense to think of little squares. It makes sense to think of kind of little chunks of kind of shells of circles. So there is our little dA, and we want to think about how would we write that in terms of a tiny change in r and a tiny change in theta. Well, the tiny change in r is straightforward. The d theta, if you want this length over here, because we'll be working in radians, the length of that there is just whatever my radius is times the little change in angle. So out of this, we get that my dA, if I'm working in polar, is going to be, so if I'm changing from dx dy, which is my dA, it's going to be the same as having r times dr times d theta. So we're almost ready, I think. Okay, so let's make our switch to polar. So we start out, we have 3 steps. And you can do them in any order, but I like to do the hardest thing first. So we want to change the limits, because our limits at the moment involve x's, and we don't want that. Let's draw out the area that we're interested in. So our lower limit is minus root of 1 minus x squared, which is this purple line here. It's the lower half of a circle. So let me just mark that. Okay, and my upper limit is 1 minus x squared. Let's check if I'm getting this all right. Okay. Happy with me so far? So, and I'm integrating, that's y, and x is going from minus 1 to 1. So basically I want everything inside this circle. Yes? Now let's describe that in terms of r and theta. How do I want r and theta to change so that I get the area of the circle? So remember, my radius starts here and it measures outward like that. So what will my radius limits be? Where would it start? So my radius is going to start at the center, and I needed to have all the radii all the way out to this circle here, which has radius 1.
0 to pi.
Mm-mm. Do you
Oh,
think
radius.
radius?
Oh, sorry.
So my radius is going to track out a little thing here and 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 here. It measures out in this direction. And we want to go every little step between 0 and this radius here, which is 1. So our radius will be 0 to 1. So it's a little trickier to see than x and y, but we'll get there. And then we need to think about what angle do we want to sweep out. So for every radius that we're at, we want to sweep out the full circle, which is 2 pi. Yeah. Okay. So our limits are going to change. Now we know these are our limits for r and theta. Changing our integrand, we already know that we use r squared is equal to x squared plus y squared. So we're going to get 1 minus r squared. And we want to change our differentials. So our dx, dy, we know goes to r, dr, d theta. Okay? So let's put this all together. Our volume, which was this thing over here, I can take this picture. Oops. Okay, just so that we can see it. So now I'm integrating with respect to, so I've changed these limits. Well, sorry, let me rather just write it down. So my r is going from 0 to 1. My theta is going from 0 to 2 pi. So I'm just picking that I'm going to integrate with respect to r first. If it turns out I screwed up, we'll switch. Now I write down my integrand, which is 1 minus r squared. And I need to have my dA, which is r dr d theta.
Why is it r dr d theta or not just dr d theta?
Because of what we said up here. We're thinking of that as a little square which has some side length times dr. What is that side length? It's r d theta, it's not just d theta.
Okay.
Because it's going to change depending on how far up we are.
Okay, thank
Yep.
you.
And I think you will agree that that is a much friendlier integral than the original thing that we had. Okay. So the thing to practice out of all of this is the 3 stages. The first thing is you change your limits. So this is in x and y, and you need to figure out what your equivalent r and theta limits will be. Then you need to change your integrand. In this case it was pretty straightforward. Then you need to change your differentials, which means remembering that you have a little extra r that comes in over here, which is always slightly weird. And then finally you put it all together. Okay. Yes? Okay. So I would have loved to have shown you this because it's one of my favorite dinky little tricks, but it is just, it's the integral of a Gaussian, which, as you know, you can't do, right? But by being very cunning, you can. And if you read the notes, you'll see how you do it. But the trick is that you... I'm going to show you quickly, because it's so cool. Okay, all right. All right, so it's going to be very hasty, but here we go. Here's the integral we want to do. We don't know how to integrate that. But if we look at I squared, that's really this. Okay, I've just taken the integral and I've squared it, right?
Why is there y?
So why is there a y? Because it makes sense to have different, they are different variables. I could have called it anything. But now I can combine these integrals. Yeah? Okay, switch to polar. And do some cunning stuff with your limits that you can check that out. But notice I've gone from an integral I couldn't do to an integral I can totally do. And you will find that you can in fact do this. You can check your limits and you can solve it. The only thing to remember when you get down to the bottom here, do I have my cunning solution here? Is that what you've ended up with is I squared, so you need to take the square root, and that will give you the original integral that you had. Just like that. See? Polar coordinates, super useful. So please do that at home. It's fun, and it comes out to a very nice answer, which you should know by now, like root pi. So, yeah. And what I like about this is, I don't know, whenever I was learning about Gaussians, I was like, why is there this pi coming in? Like, how does E know about pi? This just seems weird. But when you do it like this, and you see that you're actually working in polar coordinates, you can see why a pi might come out of there. That's kind of cute. Okay. I just get sidetracked by the beautiful things. It's a pity. Okay, so this is an example that again, so basically as you get a little more experience, as soon as you see things that are involving spheres or cylinders, things like that, your spidey sense will start to be saying to you, I really don't want to be working in Cartesian coordinates. Polar is going to make my life better. So what do we want to find? We want to find the volume of the solid region lying inside both this sphere and that cylinder. Okay, what does that look like? GeoGebra will help us. Okay, it's this crazy thing here. So here's my sphere in green and my cylinder in purple. And if you imagine, it's kind of like I've taken an apple core, but I haven't gone quite in the middle like I was supposed to. I've gone down the center. So I've got this funny shape coming out here in orange, yellow. So you can change your sphere into polar coordinates and your cylinder as well. And then a trick that is sometimes useful is to notice there's a lot of symmetry going on here. So if I think about kind of just this part here, I've really got 4 of those. So make your life easier and just calculate the volume of this red thingy here and multiply it by 4 will give you the thing that you're looking for. So you can check this at home and make sure that you get that answer. Okay.
I don't see how we have 4 of that shape, so could you explain again what the shape is?
So, okay, you've got to imagine you've got a sphere, and I've taken a core out. So the shape, the yellow shape is what I've got.
Yeah.
But it's symmetric around if I just cut my sphere in half.
Mm-hmm.
I've got 2 halves that are the same.
Yeah.
But it's also symmetric if I'd cut it this way.
Okay.
So I've got 4 things that are the same.
Oh, I see.
I mean, in slightly different orientations. So I've got this mirrored there, and then I've got this mirrored down here, and that one mirrored down there.
Okay, so you could have like that and then like that.
How did you get the integrand, like the thing under the square, in your volume integral for a squared minus r squared?
Just
It's the equation for C of the sphere. R squared plus Z squared is equal to 4A squared.
Okay.
So I realize I've gone through this very quickly. There is going to be some time that you need to take.
So just a question. Polar coordinates are not in the midterm, right?
No.
Okay.
I will
Starting the final, yeah.
Quite kind of.
Anything that wasn't in the midterm is in the final.
So this would be in the final.
Yes. But I would recommend that you spend some time playing with polar coordinates before the midterm, just because it's kind of like doing a little bit of extra work before you run a marathon. It's going to help. It's getting your head around this kind of stuff. But if you don't, that's also fine. Okay, so more stuff that I didn't even mention in the intro. For interest only, remember change of variables from single variable? Well, you can do the same thing. And in fact, we just kind of did. But more generally, you can do change of variables in double integrals. You can read about how to do it, but this is not in the midterm or the final. But it is quite useful going forward. Okay, how are we doing? Need a break? Need a little head break? Okay, what's our time? Okay, 3 minutes. Just go and make some space so that I can pack more stuff into your heads.